Test. Good.
Professor Anja Feldmann. Anja is currently the director at the Max Planck Institute for Informatics in Saarbrücken, Germany. Her research focus is on internet architectures. Prior to that, Anja held faculty positions at University of Saarland, TU Munich, as well as TU Berlin. Anja got her PhD from Carnegie Mellon University, and after which she did a stint at AT&T Research before moving to faculty positions in Germany. So Anja had a very distinguished career. Her research focused on internet measurement, traffic engineering, traffic characterization, and debugging network performance issues. She has also done some pioneering work in intrusion detection and network architecture. In fact, growing up as an internet measurement researcher myself, her work was quite inspirational to a generation of people who started working in the space. Her research is instrumental, or was instrumental in establishing the rigorous science of internet measurement. Anja won a number of distinguished awards. She's a member of the German Academy of Sciences, Leopoldina, as well as a member of the supervisory board, that is a board of directors at SAP. She's the recipient of Gottfried Wilhelm Leibniz Prize, which is one of the most prestigious and the highest endowed research prizes for exceptional scientists in Germany. She also won the Berliner Wissenschaftspreis. She has chaired pretty much all the top-tier conferences in networking, including the ACM SIGCOMM, ACM IMC conference, as well as the HotNets workshop. So without further ado, Anja, please take it away.
Thanks, Krishna, for this kind introduction, and I'm very happy to be here and to talk and tell you something about the research that I've been doing over the last 20 years. So, I called this the internet a complex system at its limits because when one does do internet measurement work, one observes what the heck is going on, and one also sees all the things that go wrong, which is the motivation for this title. So I will try to show you the positive as well as the negative aspects of the internet. But before doing that, I want to tell you a little bit about myself. Well, basically, I started everything back in Germany, and I got my diploma, because we didn't have bachelor and master at that time yet, in Paderborn. And then I said, oh, let's explore the world, because, hey, why not? And I went to Carnegie Mellon University to the US. So that was my first part, and it really paid off to say, hey, it's not all in my country, I want to expand my view. And then after I got my PhD, I kind of said, what the heck do I want to do? Indeed, even when I went to CMU, it was like I told my parents, oh, I just want to go to the US for 1 year. And they were like, oh, are you finally coming back? And then I got an offer for a postdoc position at Bell Labs, and I said, oh, that sounds intriguing, let's do it, rather than going back and doing my postdoc in Germany. And that was actually quite nice, because back here, I did all my work on algorithms. I was a theoretical computer scientist, which is also my motivation for asking yesterday the question, what's the difference between an algorithm and a heuristic? Because that actually does matter, and a lot of the stuff that currently is going on in machine learning, etc., is still a lot of heuristic. And understanding what hammer to use and how to apply it is actually critical. So I was doing all this theory, and then at AT&T I got more and more involved in actually doing networking. And then everything was really fun. It was the hype curve. Everything was like internet, big thing. And then I suddenly got an offer from Germany, and I moved back. And I kind of left AT&T while it was really good before it went downhill. Indeed, one of the things to, I guess, keep in mind in all of these things is these research labs, when they're on the setup, they are really excellent places to be. But don't count on even established research labs such as this one over here to exist 20, 30 years down the road. Be flexible. And a lot of people, even at Microsoft, at various different areas, who knows about Google, who knows about some of these other places, already noticed that. Now, at the university, at that time I said, oh, Saarland, Saarbrücken, it's a small town. I actually want to go to a bigger town. This is what I did. I actually switched over to Munich, and from Munich to Berlin. Indeed, the move to Berlin was motivated by the fact that being at a university is quite nice, but having access to real networks is something extremely valuable. And so I said, I really want to get back my hands dirty and really work with an operator. And Deutsche Telekom was setting up a research lab in Berlin at the time in connection with the university. And I said, oh, T-Labs, that sounds really good. And I did that. Was like really supported by the management, really good. And then the administrator kind of looked at it and said, oh, you're wasting a lot of money on the, and core networking for a network operator. No, that's uninteresting. We need apps. We need startups. And so I kind of only switched over to the university side. So the lesson learned here is take advantage of the opportunities that are there, but don't be disappointed if they actually go away. Move on. And then this opportunity came up over here with the Max Planck Society, and at that point I then kind of realized, my interest had kind of switched slightly in the sense, also my private interests, in the sense that I have my hobbies, I have 3 horses. So I really like horseback riding, and driving out to the stables for 30 minutes plus traffic jam is quite a pain. Doing it on a more rural area, 10 minutes, 5 minutes, is much more of an advantage. And certain things also with regards to the funding situation and much less teaching at a research institute such as Max Planck is really useful. And it's really great to be able to work with great colleagues, both within my own institute as well as our neighboring institute where Krishna is at. And that's really a lot of fun. Find the colleagues to work with and enjoy doing it, work together. And so what do? We're basically, research topics are the internet measurements, future internet, wide area data analytics, and I'm basically hiring at all levels. I'm looking for interns, I'm looking for PhD students, I'm looking for postdocs that want to actually have academic career or kind of move even to research labs. And I'm always open for furthering their career. Now, that much as an introduction. Internet. What do I find so fascinating about it? It's a man-made system, which means that it all started out with these 5 nodes over here. And since then, it has grown into this whole thing. It is a highly engineered system. It is well specified. We should, in principle, know every single bit why it's being transmitted. It has very simple component, best effort. It forwards some packets. If it doesn't forward some others, who cares? It will be retransmitted. It has the so-called dumb core, the packet switches. Yet, it has evolved. It's been growing, it's been growing, it's been growing. It will continue on to grow, it will continue on to grow. It's a moving target, which means the problems won't stop. There will always be research topics in this area. Because when it's changing, the assumption will change, we have some new stuff to look at. And it has the smart end systems, the computers, which are also growing, which are also changing. These days, it's not these guys anymore, it's kind of these guys. But it also has many, many, many different players. And I can just list a few of them. And I'm kind of reviewing some of these players over here because of the terminology as well. So basically, we have all these various different autonomous systems over here, which are operated by internet service provider. Now, the way that they interconnect is they actually buy connectivity from other networks. So you have access networks that are paying for having connectivity here. Now, these guys over here, each AES operates and determines the configuration within their own network, and they are optimizing it for efficiency. But they can't necessarily optimize across these different autonomous systems. These are being interconnected either by direct peering, such as over here, or via so-called internet exchange points. These internet exchange points are basically big layer 2 switches across which you can easily establish interconnectivity between different autonomous systems. And examples are D6, AM6, D6 is in Frankfurt, AM6 is in Amsterdam, London 6, India has some, so it's like these are all over the place. Now, of course, that's not sufficient. We also need the content, and content is king. You have these data centers that are all over the world. They are in different parts of these networks, and these are often used then by other cloud providers, such as Amazon, Microsoft, etc. Now, on top of that, you have these content distribution networks that are basically building content distribution across all of this infrastructure so that the users can download the data as close to their location as they are to make that efficient. And what do? They're doing application layer multicast. So, in summary, you have many, many different players. It goes from the infrastructure over the application providers, over the various different devices, the users, which goes from all these kinds of places. And that makes it fascinating, because all these players have to work together so that we can actually get the service that we want. Now, the problem is, every single of these players has their own goals, which makes it fascinating, but also difficult. So, what are the challenges? If we go back to this 5-node network, then we see that the internet was actually an open cooperating system. There were no evil guys out there. This has changed. The other part is it wasn't designed to actually be a system that is highly interacting across the different layers, across time, and across different locations. They are all there. It plays a role. And of course, what would happen if the internet wouldn't work anymore? Would we have power? If we don't have power, we can't reboot the internet. If we don't have power, we don't have fuel. We can't go anywhere. Our economy would go. I hope it never happens. But these systems are all interconnected. And in that sense, the internet has become a critical infrastructure. So how do I do my research? The way I do it is I want to understand what the heck is going on in the current internet. I don't want to speculate about it. I don't want to have to say, oh, according to Cisco, the mobile data will increase by that much. Cisco is the network vendor. They are not operating networks. I want to understand this myself. And then that gives us research opportunities in itself, because we need new network measurement opportunities. We need to figure out which data correlations are real and which ones are just coincidental. Then we need to actually analyze all of this. And we're talking about terabytes of data. We are not talking about megabytes of data. This is big data analysis at scale. We want to find out what the bottlenecks are. But then we can go back to the fact that in networking, we actually know what the heck is supposed to happen. We can actually say, did this indeed happen? Does it actually, the explanation that we have make sense? Because we can do what-if kind of analysis. We can simulate the network. We can verify it. We can look in the lab. And then we can think about what kind of protocol enhancements might make sense and evaluate that in realistic settings. And I will give you some example of these. So, what I've prepared here are various different topics which go from some of my initial work on network invariance over to some of the ongoing work on software-defined networking and also some other stuff. So, network invariance. I basically did my PhD on algorithms, as I mentioned. And I did competitive analysis, which is worst-case analysis for online algorithms. At some point, I asked my question, do I really need to do worst-case analysis, or shouldn't I be doing average-case analysis? And I did my first network measurement. I just put a sniffer on the CMU network and actually measured, something that you can't do anymore today because of privacy concerns. But I just did it. And I asked, so what do we have? Do we have habitat, which means really skewed distribution, lots of small and lots of long ones, or do we have nicely averaging? And of course, everything is habitat, and so that's the way it started. Now, why is that important? Basically, when you look at network traffic, the one thing you will find is that these habitat elements create so-called self-similarity concepts, meaning the traffic is much more bursty than you would assume. Self-similarity basically means that, like in this picture, independent of how you zoom in, it will always look the same. You will always again find the Mandelbrot here. In terms of traffic, it means that the variability, as you increase your aggregation level, won't decrease, which means that you need larger queues. If you don't have the queues, you still get bursts of packet losses. And that was basically shown on IP packets. It was shown for, and we showed it for TCP connections and for flows. But it's not just at the packet level, but across various different protocols. And it plays a role because the variability actually matters. If you do simulation just with long-lived TCP connections, you're completely unrealistic. And does it mean it's everywhere? No. Humans don't behave according to habitats. They behave according to nicely exponential distributions. So you still have your old queuing theory on that level. Now, it's not all self-similar, because if you look at that, the explanations only have to do with the arrival processes. The TCP elements of it, the way that packets are being scheduled, are not part of this whole process. Yet, if you look at it in more detail, you will find that it's not the same fractal dimension everywhere, but it actually differs. And that is due to all of the TCP elements. And that's what we basically showed later on, in the sense that over here, not all the same kind of elements are here, and that has to do with the fact that you have many different RTTs, many different elements, so there is much more structure at the smaller time granularities. Why does it matter? The variability is something you need to keep in mind when you're doing evaluation. You have to deal with these short guys, because the short guys are not subject to TCP congestion control. They will always arrive in bursts, and so you have to account for that burstiness, whatever you do. So choose your evaluation setup accordingly. Let's go to revisiting assumptions. What are some of the typical elements here? One of the things that one should keep in mind is the internet is all about change. And so certain things that might have been valid 5 years ago may no longer be valid. And one of the ways to kind of look at this is always by looking at the application mix. Killer application. In '93, when I did my PhD, there was hardly any web traffic. 94, it was about 10%. 95, 96, 60 to 70% all web traffic. So basically, the protocol that dominated the internet changed completely. Peer-to-peer, 2000, hardly any. 2009, the BitTorrent designer that I talked to told me, we are taking over the world. Did this happen? No, it didn't. Web traffic came back. Why did it come back? Well, the problem with peer-to-peer networks is the music industry complained. They really kind of objected to the fact that people were downloading everything there. They were saying, hey, I actually sue you. And because of that, things went back to content distribution networks, and that's when the content distribution networks rose and peer-to-peer went down. So you went from distributing content via peer-to-peer to using content distribution networks, which is why we actually have quite a bit of flash video over here now being transmitted via web. Indeed, most of the bytes that are being transmitted in the web are video. And this is still the case. Web and secure web are dominating. But are they dominating everywhere? No. You cannot say just because web traffic is dominating that for every single specific link it will be dominating. Rather, you have to see what kind of links are you looking at. For example, if you're looking at a hoster, then there might be quite a bit of BitTorrent traffic still going on. If you're looking at an eyeball network, it depends where you are, what kind of eyeball network it is. You may still see quite a number of peer-to-peer links. On the other hand, if you're looking at the CDN connectivity, there might only be HTTP, or by now HTTPS. So different vantage point, different application mix. So what about interdomain traffic with spoofed source IP addresses? Well, this is all about where things can go wrong. What is the problem with spoofing? The problem with spoofing is that the source IP address that you're using over here, when you're sending a packet, in some sense, you don't need it to deliver the packet. To deliver a packet, you only need the destination address. You can put it like when you send a letter. You need to put down the destination address, but which source address you're putting on the letter, who cares? It will still be delivered. The same is true in the internet. So everybody can fake the source IP address. So IP source address spoofing is being used to actually do almost all of the DDoS attacks that you see in the internet today. Because the way that it's being done is you send a packet using a spoofed source IP address. The receiver is receiving it, sending a larger packet back to this IP address. And so the DDoS system is getting all of these traffic from all over the world, but not from the guy that is actually DDoSing somebody. And because the intermediate node is sending a larger packet, the DDoS source only needs to send a very small fraction of traffic. Now, how would you mitigate that? The problem is that you're getting a lot of traffic at the destination that is being spoofed, but you don't know really where is it coming from. And so to mitigate this, we should eliminate spoofing. But that doesn't really work well. The question is why? The problem is detecting the spoof traffic is hard, and we wanted to see to which extent we can actually do that, at least give some lower bound in terms of how much spoof traffic there is. So what do we want to uncover? We want to uncover packets with those source IP addresses that are not of the interface of the sending host. So whoever is using an IP address that they're in some sense not supposed to be using. What kind of features can we leverage? We can leverage address information, and we can leverage routing information for that. So what should we never see on the internet? If this is a whole IPv4 address space, we can divide it up. On the one hand, we have the routable address space, and then we have the so-called bogon. Those are all the ones that are private address space, reserved address space, multicast future use, IANA reserved, etc. What's your guess? Do we have bogon traffic on the internet? Yes, for sure. The question is just how much and why. Next, within the routable space, we actually can look at the routing tables all over the world that are being distributed at all these different locations that record the routing traffic and say, this prefix is routable at least in some place of the internet. But there is quite a bit of address space which is still in this unrouted part over here. It's been assigned, but it's not yet in use. Now, this is still autonomous system agnostic. But then we can also kind of look at within the routed space, and there are some addresses over there that an AS should never observe, where they shouldn't be sending out traffic from. That is now AS specific. And identifying this part over here, which source IP addresses an AS should never send out, is actually non-trivial. So, who is allowed to send what? What we wanted to do is focus on the AS level metrics. We wanted to do lower bounds because we didn't want to say, oh, we are doing an upper bound, but a lower bound to just estimate how large of a problem we are. So for that, we need to determine this set of invalid AS-specific elements here. Now, why is it difficult? Let's take a look at this kind of topology over here. Here we have the public internet, we have various different ASs, and we have some more ASs back here. So, over here, if this ASA is announcing prefix P1 and P2, then of course the traffic over here can come back this way. And so, this is legitimate traffic. These are legitimate source IP addresses for this AS over here. So, they are in the list of valid prefixes. Now, if this AS over here announces P3, which is being forwarded by ASA, then of course P3 should be in this list. But of course, if ASD is now announcing P4, P5, P6, which is being forwarded by this one over here, which is being forwarded by this, then these are also part of this list over here. So that means in this case, all source IP addresses which are not part of this list over here should not be seen over here. Now here, in this case, it is still possible to list all of these prefixes. But once you're at the tier 1, the tier 1s are on top of the AS level hierarchy. That means that all of the customers of that tier 1 and the customers are legitimate source IP addresses, which pretty much means the whole address space. And the problem is, if over here, then suddenly some ASs kind of agree to peer, it's very hard to verify which IP addresses are valid or not valid, because this ASD has no way to communicate to ASA. These are the prefixes that I can actually announce, which is also the reason why filtering is so difficult. Now, how much traffic do we have? Bogon, 31.63 terabytes within a month. Unrouted, 38.29 terabytes. Invalid, a lot more. Now, if you look at it in terms of packet sizes, you will find Bogon is mainly small. Unrouted, invalid, is also mainly small packets. Regular traffic is split. You have 50% small, 50% large packets. And then you have a little bit in between. So the total amount of spoof traffic that we can pretty much identify as lower bounds is fairly small. But the impact can be big. Amplification. And this is a lower bound. We were extremely conservative in terms of this classification. Now you can ask, who is actually contributing to all of this stuff? And you find that if you're looking at all the various different ASs, 30.29% of them have invalid traffic, unrouted traffic, and bogon traffic. So they're basically not filtering. 72% emit bogon traffic. It is very simple to filter for bogon because that's a very well-specified list of traffic. It would be very simple to do so. They still don't. Which is the reason why we see so much attacks. 53% emit unrouted, 57% emit invalid. 30% of the IXP members do not filter any of these, which is the amazing part. Now we asked why, and we actually talked to a lot of them. If you're looking at the smaller ones, for them, it's too much overhead. They don't want to make any mistakes. The larger ones actually filter more. But even there, the larger ones have the problem that filtering for unrouted and invalid is actually very, very difficult because they cannot compile the list, which really means that we need to get a better way to know who is the customer of who is allowed to actually send traffic, and that we need to push this problem of filtering all the way to the edge so that everybody is cleaning up. Now, you may want to say, wait a moment, why is there so much bogon traffic? A lot of the bogon traffic is actually due to routers being wrongly configured and suddenly sending out traffic with 10 at private address space because the trace route, because of other kinds of things. So all the wrong configurations that you can see out there in the internet. Now, in terms of traffic mix, in terms of destination IP address, you see TCP, regular traffic, bogon, unrouted, invalid, UDP destination. Oh, wait a moment. In invalid, we see so much for port 123. Guys, do you know what port 123 is? You don't? NTP. That's your amplification traffic. Destination, mainly HTTP, and that basically hints at flooding. If you look at where is it coming from, we can also see different patterns which are typical of these attacks. Selected IP addresses, specific source IPs, many packets with few source addresses, random spoofing across the whole address range, flooding attacks, etc. So if we look at it, for bogon, we see that it's going across everything. Unrouted, it's a few source IP addresses. Invalid, it's mixed. In terms of who is being spoofed, you see certain prefixes that actually see much more space. So distinctive peak was actually at 183./8 over here, mostly Chinese ISPs. Almost all traffic is going to NTP server, and it's NTP attacks against these ISPs. So what we did is we did do measurements, we observed, we were asking a specific question and then answering it. Global signal, many vantage points, yet hard to determine this valid address space. By doing so, we were actually doing big data analytics, using it as a tool to answer questions. So why is it important? It allows us to understand the attack patterns. It looks at the critical infrastructure and how it's being fooled. And it also tells us something about the evolution and the problems that we're having. Now the question is, of course, once we have these attacks, how can we mitigate it? DDoS attacks are all over the world. And here are just a couple of these newspapers tickets. And there could be many more here. This is just selective. Now, one of the things that exists in the internet is actually BGP black hole. What is the core idea behind this? The core idea is that if you have an attacker that is sending you unwanted traffic, like the one that we just talked about, to this target server over here, then this might actually get overwhelmed here. It cannot handle all that traffic. So the good guy over here that wants to actually connect to it cannot actually get any connectivity anymore. So the way to actually handle that is that this guy over here says, oh, I'm observing too much traffic here. Let's say I want to ask this guy over here to drop the traffic to this server by sending a BGP announcement with the community tag here. What will then happen? We are basically blackholing this prefix, saying this guy AS3, please drop all the traffic on behalf of this AS over here. So we're using a blackholing community to do this. This is being blackholed here. So this guy can still reach the server now. Because this is being blackholed here, we can actually forward this. So this guy can actually blackhole it, and we can drop the traffic as early as possible so that it doesn't even get delivered over here. Note, this is violating network neutrality because we are suddenly dropping traffic on behalf of somebody else. We are not delivering the traffic. There are various different specifications for that. And we wanted to ask, is this being used? And yes, it's being used. Overall, we see from 2014 to 2017, over here, the blue lines over here, it's being heavily used, and you see some spikes. These spikes are actually interesting. DDoS attacks, CREPs, DNS attacks, Turkey, Rio, Mirai. So they really correspond to some of the known DDoS targets. Where are they sitting? Well, not surprisingly, in some part of the world. A lot of them belong to content providers and hosters. So basically, blackholing is on the rise. It is very effective in terms of dropping some traffic early. But it is a very, very coarse-grained instrument. You're basically dropping all traffic to an IP. Because it's so coarse-grained, we just proposed a mechanism to say, don't just say drop traffic to an IP, but drop traffic to an IP plus port number. Be much more specific. And we showed that this can be realized at an internet exchange point and have a much more selective way of doing it. So instead of using the hammer, which is this huge, use one which is this. Be much more specific. But if you have this ability to actually drop traffic, then this can also be app used. Because if there would be an AS in between, it could actually just attach the community and ask this guy to drop all traffic to an IP. So you can actually use this nice mechanism, which helps you to drop traffic, to also drop traffic that shouldn't be dropped. And we just showed that this is also possible in the internet. So this whole mechanism of these communities can be heavily app-used. And these communities here, they are just tags that any router can add on the path. There's no semantic to it. There's no validation. There's no security for those. We're now adding security by validating the sources, but we're not validating these communities. So there's yet another problem in the routing environment over here. And that was just a paper being presented at yet another conference. Why do we need this? Well, it is nice to be able to protect our infrastructure with dropping traffic, but it's also yet another problem for security. Now I want to briefly talk about software-defined networking and point out some of the problems there. So the concept of software-defined networking is to say, hey, let's not give all control to the Ciscos and the Junipers by having them sell us boxes, but rather separate the routing software from the routing hardware. Because the hardware is all about forwarding packets at line speed. That's very difficult to actually implement oneself. doing the routing, that's software. That should be able to develop independent of the hardware. And that's the core concept of software-defined networking. It's very useful to overcome architectural limits, but it also has new problems. And I just want to outline one of them. So basically, software-defined networking can be extended all the way to the edge. And all of the data centers these days really use the concept of software-defined networking by having virtual machines, a virtual switch to interconnect all these virtual machines. And the most common software to be used here is the Open vSwitch software. So you have a VM, you have a virtual switch, you have DPDK to actually do the fast forwarding, you have a virtualization network here. Open vSwitch is the most popular one, and some of our colleagues said, oh, let's apply fuzzing to it. It's software. And of course, if you apply fuzzing to a nice piece of software, what do you find? Bugs. So we basically found a buffer overflow vulnerability in an Open vSwitch, and that leads to remote code execution. What was it? It was a problem in the MPLS header, where you're basically parsing the whole thing, and they forgot that there should be a limit to that. And they didn't check that. So a long label stack led to a stack buffer overflow. Why is that? Basically, they were parsing all of these various different protocols, and adding one more parser and more parsers and more parsers to it creates problems. And we basically showed that this is exploitable. Why? GCC does not place canaries for these vulnerable functions. So what can you do with that? You can actually use that to do a large-scale compromise. So we basically went from sending out one packet over here from a VM of our choice, and you can always rent a VM in a data center. You can always send out this packet. This took over the kernel over here. From the kernel, we went to the controller node. From the controller node, we went to all nodes. Basically, this is all about how to take over a data center in less than 2 minutes. Oops. What was the problem? You have a unified packet parser here, a centralized parsing for all these various different protocols. This is how many different protocols you have to support. That's error-prone. And it's increasing the number of protocols that you have to support. You can actually send any data that you want from a VM. There's nobody here checking that you don't send malformed packets. You can send packets with spoofed IP addresses. You have a co-location of your hypervisor with your virtual switch, which means if you can have a bug here, you can take over your kernel. You have centralized control, which means once you have infected your centralized controller, you can go to everybody. So, long-term evolution, it is somewhat of a problem. Now, with regards to the outlook, I want to actually talk a little bit about flow stream here. Basically, in networking, we cannot say we don't have data. Rather, we have an abundance of data. Now, the main problem that we are having is we are writing Perl scripts, Python scripts, or something like that to actually answer queries about networks, which is something which doesn't allow interactive exploration of this data. But rather, it takes days, weeks, before you have an answer. That doesn't really scale well. Yet we want to be able to answer questions such as how much spoofed traffic is there in a very short time period. So, for network management, we really need performance and security, and we need flow queries really, really quickly on all of this data. in addition to it, if you look at all this data, it's terabytes. It's coming in, it's coming in, it's coming in. Any system that we deploy, whatever money I spent on this space is limited. So I have to delete traces, which I really hate to do. Also, you may not be able to actually transfer all data to a central location. And we need more query support. We want trace management. We want complex queries, drill-down queries. If I know there is a lot of traffic to an IP, I want to know where is it coming from, etc. Now, the problem that we see is that we have all of this data. What we want is we want these routers to send this to local locations where we want to summarize this data in such a way that we have a self-adjusting data structure that captures the essential pieces. And then we want to be able to share these to a central location. Those are much smaller, so that we can then add time and location information and still query this whole data structure. And we basically want to do this across different feature sets, because we do not just have destination IP addresses, we have source and destination IP addresses, we have IP addresses and ports, etc. So, luckily, we actually have a hierarchy here. We have these /30s that are part of a /24, which are part of a /8. And we can do that for ports and IP addresses. We can build up these hierarchies here. Now that means if we don't have a lot of popularity here, we don't need this node. We can actually delete it, and we can actually summarize this information at the next level up. If we have a lot of flows over here, we can actually expand it and add more nodes below it. And so, the key idea here is we want to keep statistics for these subnodes in such a way that it's a self-adjusting data structure that figures out automatically which are the heavy hitters and dynamically scales this to be able to expand the popular ones and cut out the unpopular ones. Once we have that, what you can observe here is that we can add more features to it. We can add time. We can add location to it. These trees are mergeable, and you can compute differences. And we are currently working on actually setting up such a system to be able to have a scalable data analytic, to be able to interactively query these nodes, because now you can suddenly summarize a day worth of data with just 2,000 nodes. You can query that. That's efficient. You can set up a database on top of that. We designed a flow query language which is similar to SQL, or kind of based on SQL-like queries, and this is suddenly becoming memory efficient. And that is some of the ongoing work that we're having. So in summary, I'm enjoying my work doing network management because the nice part is here, with network traffic, there's always something new appearing. There's something new happening. And that's what makes life so damn interesting. Thanks for your attention.
Anja, for the fantastic talk. We have time for some questions.
That's a very interesting talk, thank you. My name is Shanti. I teach in one of the engineering colleges here. Most of the problems that we see seem to be because of the host-based addressing that we normally have on which the internet is based. There are proponents of other things. You also mentioned that content is king. There are people who say information-centric networking seems to be the solution to most of the problems like IP spoofing, Van Jacobson and other people. What do you think? Do you see the future internet having in some form alternate architectures like ICN, at least as silos, if not in the core network?
Okay, I definitely do see alternative architectures, because I believe one of the things that will happen are cloud nets, where we will be able to set up a specific network for a specific application. Do I believe that ICN, information-centric networking, will happen? Well, what is the idea of information-centric networking? The idea is that you will push content into the network, and the content will move towards the guys that are interested in the content in some ways automatically. Honestly, I don't believe that. The reason for that is that the guys that are providing the content really need the information about who is accessing the content, who is interested in that content. They depend on that information. And information-centric networking doesn't account for that. So I don't think that people will just push their content into the network and let the network deliver it. Rather, content distribution networks are content-specific distribution networks, and they give the statistics back to the guys. They have a monetization model, namely advertising, that kind of works. And therefore, I don't believe in ECN. I believe in content distribution network. I believe that we will see different overlays on top of the internet, or maybe natively, for different kinds of applications. So I can easily see specific cloud networks for gaming, because that needs a different kind of architecture, a different kind of a scheme. I don't see it here.
Yeah, so you talked about black holing. I think it looks like a very interesting strategy, but how will it handle in a real-time situation when we are talking about some natural calamity or disaster, and people are trying to, reach each other or go through that? Can it not be considered by the servers as somebody is trying to, spoof of something, a DDoS attack or something on the local ISPs and all that?
Okay. In the disaster area, then we don't need black holing or something like that, because we struggle to set up connectivity in the first place, and people probably won't worry about DDoS attacks or any of those kinds of things. When you have a network that is heavily subjected to DDoS attacks, you will see the fact that there are links that are overloaded, and people will do whatever they can to reduce the load on that network to kind of make that part of the communication real again. They will know which IP addresses are being affected because they see which servers are overloaded. They can almost automatically trigger the black holing, and you can see that that is happening. And the more finer grained we make this kind of black holing communities, we can actually more and more automate it. And it seems like that there are at least some content providers that are quite willing to take advantage of black holing capabilities being offered by the networks.
Thank you.
Anja, thanks for a great talk. Quick questions. You've seen internet evolve over the last several decades, right, since the inception, right? Now, you've seen also the changes happening in the traffic of the internet, right? We know that video dominates, but in the next, in the next years to come, or maybe next 10 years, how do you see the traffic evolving? I mean, what are going to be the fundamental change that you see or you expect in the years down the line in terms of internet traffic?
One of the things is we don't know what will happen. It's like, I think peer-to-peer, when it first came up, it really surprised people. Nobody would have predicted that. The web, when it came up, nobody would have expected that. So there might be a new application coming up that we don't know yet. One of the things that we do see is that more and more of the traffic is moving. In some sense, what we used to have is we used to have the hourglass model with IP in the middle. This IP is in some sense being replaced by HTTP. More and more applications are moving on top of HTTP, even though HTTP may not be the ideal transport protocol for them. But they are using HTTP as a transport protocol. At the same time, HTTP is moving to HTTP2, which is moving on top of QUIC, which is a new way of actually doing not just video over TCP anymore, but suddenly moving over to UDP. So I expect that the amount of UDP traffic that we see will increase drastically, but this is not plain UDP traffic, which is not subject to congestion control. There is congestion control there. So we will see a drastic shift in terms of traffic, going away from TCP, moving over to UDP, with all its advantages and disadvantages. But it's also the time that we can now think, hey, what should the congestion control be? Because this is a protocol which is currently under design. Do we really need to transmit all bytes in TCP in a reliable fashion for video reliably or not? And we are working on some extensions to QUIC at this point.
Yeah, so I have, hi Anja. I have a couple of questions that are somewhat related. So, we are in 2019, and we are still talking about BGP, black holing, and prefix hijacking, and so on, and we are still suffering problems like this. Why is it taking so long, and why is it so difficult to fix this? What is the issue? The second related question is, you talked a lot about network measurements, and I've done a bit of network measurements myself. I used to go to IMC and so on. What has been the impact of all this measurement work? People come up with interesting observations about phenomena that are happening, but have those led to actual fixes and improvements in how the internet works?
So one of the reasons why it's so difficult to actually change BGP is all the many different players that we have. We would have to change every single AS and every single AS how they are actually interchanging the routing information. That is the core backbone of a system that is actually working. There is the whole thing, never change a working system. So actually changing something that is still working is really, really complicated. Has the work had any impact? Well, they are moving from BGP to some secure versions of BGP to be able to at least eliminate those guys that are just announcing prefixes without the right to having to do so. Work such as the one that we are doing here can point out how ASs further have to change their management ways, in which they have to be much more diligent in terms of actually putting down filters, putting in filter lists, making sure there is out-of-band mechanisms to communicate this. Which is why we are talking also with the RIPE, the IETF community, and presenting the results there to have an impact. Now, has this work had an impact? Well, one of the things that we did while I was at AT&T is, at some point I asked them, can you give me the current topology? And they first sent me a PowerPoint file. And I said, wait a moment, I mean the current topology. The next thing they did is they sent me the router config files. I started parsing these router config files, and I found many things that were inconsistent. The first time I sent the network guys the question, wait a moment, on this router you have the OSPF weight 5, on this one you have the OSPF weight 3. Is that supposed to be like that? And that was a huge bandwidth link at the time. They said, no, we fixed it. At that point, the response time, whenever I sent them a question, was minutes and no longer weeks. And that debugger that is actually doing the consistency checks is still being induced. But these days, it's not just a debugger, it's these config files are being generated and no longer manually edited. And that made a huge difference in terms of the amount of problems that you see. Also, the traffic matrix work that we did is, it looks at automatically reconfiguring the traffic path in which we are doing it. So the measurement work had impact in terms of dimensioning, traffic engineering, etc., and not just at AT&T, but also some of the other networks. The work that we're doing right now, for example, with QUIC, we're saying, for video traffic, why actually do everything reliably? For video, hey, once you've lost the packet, you better move on. That could improve performance for a huge number of users, while also reducing the number of bytes that you have on the network. Can have a huge impact. The work in terms of pointing out that IXPs actually play a major role has changed the way that we have actually had to look at the internet topology. So it changes the way that we need to look at traffic. It changes the way that we're needing to look at some of the information. The fact that it's all web, well, it basically says, don't waste your time on peer-to-peer networks. So I think it has some impact.
Yeah, thank you for your presentation, and also thank you for your views on ICN that has been floating around for many years now. I have a question that is related to IoT. You did not talk about IoT. If you look at the future outlook, we can expect, let's say, a factor of 10, or a factor of 20, or 30, or 40 more hosts to connect to the internet. I bought my first IPv6 book back in 1996. I did not spot IPv6 on your slides. So, what is your view on how IoT as a phenomenon will impact the internet in, let's say, the coming decade? Today, we only see a trickle of data floating that is related to IoT, but it would be interesting to hear your views.
Let me take some of these questions. First of all, IPv6 right now is only about 5 to 10% of the traffic. IPv6 doesn't necessarily fundamentally change any of the things that we see inside the network. It's just longer addresses in that sense. It changes more on the end-to-end side, in the way that it gives you more control, more flexibility, better network control. With regards to IoT, one of the things that we see is, of course, an integration of the physical and the digital world. And let me just take one example here, and that is the car. The car interacts and needs a lot of local processing. But it also interacts here with the next element. And, of course, it should interact globally. And so in this kind of integration of the physical with the digital world, there are many more control loops that are possible, that are feasible, and that we have to look at. Yet, do I believe that all these IoT devices will be on the internet? No, sorry. There has to be an aggregation structure where we are taking the data locally and aggregate it. Indeed, what we will see here is that we have, let's say, no longer just a single source, but we have many different sources. There are many different targets here. It needs to be business logic, and this data has to be aggregated as we are moving along. And as we are doing so, we need to basically bundle the resources that we actually need to process this data, and we need to have a controlled flow, a data pipeline. Who gets access to the data in what stage at what point in time? This will be an overlay on top of the internet. But we have to really work on this as well, on how we are going to structure these data pipelines so that the data gets to the people that need it, but the data isn't being processed again and again, but the aggregates are dealt with, authenticated in a way that we actually have traceability and that we know which data point is influencing what. And that will be yet another challenge for moving forward on the whole elements. And that's, in that sense, thanks for your question here.
Yeah, so.
I really hate to be the killjoy, but we're running out of time. I see a number of hands raising. So since we've already given the microphone, if you can make your question quick and brief.
Yeah, thank you. In fact, she already addressed part of my question was related. But just to add an extra caveat, right? As the number of devices increase coming onto the internet, I was motivated by something that we are doing. Taking your car example, when you have put a lot of electric vehicles on the power grid, which is the equivalent, which is similar to the internet. What we are doing in the community, in the Internet of Things community, particularly related to smart grid, is very innovative business models. Whereas, so if 10 people put their cars on the network, then you have an innovative business model whereby somebody who wants a car charged fast has to pay more. Do you see some business models like that, even on the IC, on the the data and the communication side of things?
Let me put it this way. Whenever you want to do any change in the internet, unless you have a good business model for it or business reason for it to be changed, it won't happen. You can have the best idea. If you can't get a benefit for everybody, it won't happen. Now, that means that you always need to think about what would be the advantage, and not just for one player, but for multiple players. And yes, there are new business models in which you can think about doing certain things. So one of the things that we did in the past was to say, for peer-to-peer, it doesn't really make sense to get the content from somebody in China if you can get it from somebody locally. For peer-to-peer, it didn't matter. But for content distribution network, we figured out a better way for the content distribution network to actually work together with the ISPs to jointly optimize the traffic flows, which is another way in which we had the measurement work has had an impact, because this is now, after 5 years, being deployed by a major ISP in the something where at all of these data flows over here. Data is king and data is money. And so, yes, I think that we will find new ways in which access to this data can be monetized, and quick access to the right set of data that you want can be. On the other hand, in order to make some of these things, such as better, less pollution or so, you probably need to kind of have some central information, central management that actually does it, and that is of governmental interest, and so you need to get the states and the public infrastructure involved in providing the data and also in managing the data access. Sorry for not being able to answer these questions quickly.
Thank you so much, Anja. Let's thank the speaker again. We have a small memento for you.
Thanks so much. You're welcome. And I will be around for the rest of the day, so feel free to grab me.
There's an announcement. So whoever have got the travel grants, I request everyone to go to the registration desk and put their signature.